Hi, this is second lecture of the fifth unit, vector integration. In the lecture 1, we learned the definition of line integral and also finding the work done in moving a particle along a curve and the conservative vector point function, what is called conservative vector point function. These three topics we learned in the previous lecture. Now, in this lecture, we are going to learn what is a surface integral of a vector point function and some examples on finding the surface integral. The definition of the surface integral is just similar to the definition of the line integral. It will be in the same lines. I'll explain the topic to you. So consider some surface on this in space. S is the surface, and a vector point function f bar is defined on S, defined on the surface S. That means whatever point you take on the surface, if that point whose coordinates are r bar, you can always find f bar of r bar, you can find out. That's what the defined on the surface S means. Now you divide this surface into several subsurfaces. And you have some subsurface, say, yes, there are so many subsurfaces, S1, S2, S3 like this. There are n subsurfaces. A surface is divided into subsurfaces, n subsurfaces, or divide S into n subsurfaces. Divide S into n subsurfaces. Let Si be one of such subsurface. So this is Si is one of the subsurface. Whenever you have some subsurface, this subsurface will have some area. I'm calling that the area of subsurface as delta Si. And this subsurface will have some outward normal vector n bar. N bar is the outward normal vector to this surface. That I am calling it as Ni bar. Ni bar is the outward normal surface to the delta Si. So that is Ni bar into delta Si. This I can consider it as a vector area. It is a vector whose direction is perpendicular to the subsurface Si, and area is magnitude is equal to area of the subsurface. So delta Si into Ni bar is the vector area. In this subsurface, take some point. Let its position vector be some ui bar. Ui bar is the uh, position vector of any point of subsurface Si. Now, because f bar is defined on S, I can find out f bar at ui bar, I can find out. And you have one vector area which is delta Si into Ni bar. You find out this dot product, maybe cross product. And you do the same thing for all the subsurfaces. Suppose if you take another subsurface, for this subsurface, suppose this subsurface is Sk, for this Sk, delta Sk into Nk bar. This is the normal vector to that subsurface. In this surface, take one point, that is uk bar, find out f bar of uk bar and find out this sum. So you do it for each and every subsurface. That means I am doing it for all the subsurfaces from 1 to n because I divided n surfaces. I will take the limit as n tends to infinity. If I do the same thing by dividing the surface n into much more number of subsurfaces. If I divide this as n tends to infinity, that means I am dividing that surface into more number of subsurfaces. If I make it 100 at the beginning, after that say 1000, after that maybe 1 lakh, maybe 10 lakhs, like that. If I do so, what happens? The vector area, the subsurfaces area will decrease. That means delta Si tends to 0. As n tends to infinity means delta Si also tends to infinity. It tends to 0. Delta Si tends to 0, or n tends to infinity. If I take this limit, if this limit exists, this limit, if this limit exists, then this limit is known as the surface integral of f bar, surface integral of f bar on S. It is denoted by integral over S f bar dot d s bar, or you will write it as f bar dot n bar ds, where this n bar is the outward normal vector to the surface. In the fifth unit, you learned how to find out the normal vector to a surface. If a surface is given by phi of xyz is equal to 0, what is the outward normal vector? Out is outward, of course, this is the unit normal vector. N bar is dou phi by dou x into I bar plus dou phi by dou y into z bar plus dou phi by dou z into k bar. This is the normal vector. By its magnitude, if I find out that, we get the out unit normal vector. This is how we will get that. Okay, so this is f bar dot n bar ds. This is the definition of the uh, surface integral of f bar over s. Now this n bar is the outward normal, of course, unit vector to the surface, or unit normal to the surface. Okay, so this is the definition of this. But how do you find the surface integral? This is more very in this particular lecture, the main focus is on this. If you understand properly, you can solve the problems. In order to evaluate the surface integral, it is convenient to express them as a double integral taken over the projection R of the surface. This kind of things already in the um, in the third unit, we learned how to find out the double integration over a region, that we already learned. So that helps here in evaluating the surface integral. If you want to evaluate a surface integral, express them as a double integral. Whenever you have a double integral, you have to have a region R. What is that region R? Region R is the projection of that surface on some plane, maybe xy plane or yz plane or zx plane, on any one of the coordinate planes. The next question is, on what plane we need to take the projection? That is more important. For that, there is one simple thumb rule. You understand this one. The evaluation of double integral is possible only if the line perpendicular to any one of the coordinate planes meet the surface at more than one point. For example, I'll give you this idea so that this will give you a better understanding. Suppose I have a paraboloid like this. Now, this is x-axis, this is y-axis, this is z-axis, and this is something, some z is equal to 2 line. So this is the paraboloid bounded by this. Now, if this is the yz plane, for that yz plane, if I draw a line perpendicular to it, it is cutting the surface at 2 points, cutting this paraboloid at 2 points. Whereas if I take the xz plane, even then also, that means if I uh, draw a line cutting this board, then also this cuts the surface at 2 points. Instead, suppose if I take the xy plane, if I take the perpendicular to it, if I draw a line, it cuts the paraboloid at only 1 point. Therefore, for such type of problems, the projection is to be taken on the xy plane. So the evaluation of, now read this statement once again, this statement. The evaluation of double integral is possible only when if a line perpendicular to any of the coordinate planes meet the surface at not more than 1 point. It may cut or may not cut. If it cuts, it should cut at only 1 point, not more than that. Then, based on that rule, we need to take the projection. Now, if the surface do not satisfy this condition, then it can be subdivided into surface. Suppose if I don't consider this z is equal to 2, if I don't take this plane here, then it line cuts the surface only at 1 point. If I consider this plane also as one of the surface, that means now that my surface is this paraboloid along with this plane. Put together is the surface. Even if I draw a line perpendicular to the xy plane, then it cuts the paraboloid and this plane at 2 points. Again, it is not cutting the surface at only 1 point, it is cutting at more than 1 point. In such case, what you have to do is you have to consider this surface as one surface, this paraboloid is one, and plane is the other one. Consider it as two different surfaces. You split that. You subdivide that into surfaces which do satisfy this condition. If you take only paraboloid, it cuts only at 1 point. If you take only one plane, it also cuts at only 1 point. So ultimately, we take the projection on the xy plane. Instead, if I take the line perpendicular to this, this cuts the plane at more points and also this paraboloid at 2 points. So in this particular case, the projection will be on the xy plane is advisable. If the surface do not satisfy this condition, that can be subdivided into surfaces which do not satisfy this condition. So which do satisfy this condition. Condition, this is the condition. Now, if the projection, if you take on the xy plane, then this you have to remember this. These are very, very important. Integral f bar dot n bar ds is double integral over r1 f bar dot n bar dx dy by n bar dot this n ds is to be replaced with dx dy by n bar dot k bar. This modulus of n bar dot k bar. If I take the projection on the xy plane. Instead, if I take it on the xz plane, dx dz by n bar dot j bar. If I take dz dy, it will be on n bar dot I bar. This depends on your projection that ds is to be replaced with this, and then you apply the double integral. So for those who have, I think the chemical engineering students, they don't learn the double integration, but for them, they need to have some idea of finding the double integrals. So go through my lectures, double integration, and then evaluate, and then only you can evaluate the surface integrals. Right. Now, what is the interpretation of surface integral? If you find out the surface integral of a function f bar, you'll get some value. What that value represents, that is what interpretation is. That depends on what your f bar is. If your f bar represents the velocity of a fluid particle, then the total outward flux, I think you know the flux. Flux is the amount of fluid pass on per unit area. Then the total outward flux of f bar across a closed surface S is integral S f bar dot n bar ds. It gives the, if you find out the surface integral or a closed surface, then it gives you the outward flux. If the flux across every closed surface in a region E vanishes, then f bar is said to be solenoidal vector point function. So in your fifth unit, in your fourth unit, you learned what a solenoidal vector point function is. Solenoidal vector point function is whose uh, divergence of f bar is 0, then we say that it is solenoidal. Now I am giving another interpretation. If you find the surface integral of f bar dot n bar ds, if this also 0, then also I call it as solenoidal. That means there should be some relationship between integral s f bar dot n bar ds and del dot f bar equal to 0. For these two, there should be some link. What is that link? You will learn in the coming lectures. There is one theorem called divergence theorem. It gives that information. I think in previously in your fourth unit, whenever this divergence of f bar is 0, you are calling it as solenoidal. So how can you identify that f bar is solenoidal? The first case is when divergence of f bar is 0, then it is solenoidal. Or secondly, surface integral or a closed surface integral or a closed surface of this f bar is also 0, then also we say that it is solenoidal. Okay, right. Now let us solve these examples. The first one, evaluate integral over f bar dot n bar ds. F bar is given like this. F bar is some 2x square y minus y square uh, plus 4xz square. X square y minus y square plus 4xz square. S is the closed surface of the region in the first octant. He has given that it is a closed surface of the region in the first octant bounded by the cylinder and the planes x is equal to 0, x is equal to 2, y equal to 0, z is equal to 0. Y square plus z square is equal to 9. You know that it is a cylinder whose axis is x-axis. Okay, so let us solve this problem. Listen carefully. This is very important problem. Let me first copy down what the function is. You can easily remember what is the surface is. 2x square y minus y square 4xz square. 2x square y minus y square 4xz square. Those are the components of the 2x square y minus y square plus 4xz square. 2x square y I bar minus y square j bar 4xz square k bar. This is my f bar. Okay. Now the first problem what we are doing is f bar he has given. F bar is equal to 2x square y I bar minus y square j bar plus 4xz square k bar. Very nice. Now the surface is y square plus z square is equal to, this is y axis, this is my z axis. Actually, this is how your y square plus z square is equal to 9 is the cylinder which goes, whose axis is x-axis. It will be like this, but he has given it is bounded by the planes x is equal to 0, x is equal to 2, and y equal to 0. Y is equal to 0 is zx plane, this plane, and also um, z is equal to 0, that is xy plane. So I am, after cutting this part, I am writing the actual picture. Yeah, I think you are getting the idea of that. So you have a cylinder. This is whose xz plane is cut. This is xz plane. Xz plane means y equal to 0. That is this plane. And xy plane. This is xy plane. This is z is equal to 0. That is cut back side and side of it. and also the bottom is also one another plane. This is YZ plane, and this is the curved surface. So just imagine that you have a cylinder, and that cylinder is cut by uh, XZ plane and YZ plane. Two sides it has been cut through the to the center of the cylinder. Make two cuts perpendicular to parallel to the axis, and also base is one. Okay, cut the base and cut the top at a length of 2. So this x is, this is z is x, this is x is equal to 2, and because it is y square plus z square is equal to, and this is 3, y 3 0 0 3 0. This is also 0 0 3. Now this is the surface. So this is the, sorry, now I rename it the 0 O A B C D E. So it is the surface. So let S be the surface bounded by y square plus z square is equal to 9, y equal to 0, z is equal to 0, x is equal to 0, x is equal to 2. Now that S is the union of the surfaces. Union of the surfaces. One surface is O, the first one, union of the surfaces. I'll call it as O B C D. OBCD, which is a rectangle. Two, second surface is this OAED. This is also a rectangle. Third surface is the base OAB. OAB, which is quadrant of a circle. This is quadrant of a circle. And another surface is fourth one is surface, the above surface, ECDE. This is also quadrant of the circle on the plane x is equal to 2. This is the circle, this is also circle, but this is on the plane x is equal to 2. This is on the plane x is equal to 2. And also this surface, fifth one, is A, B, C, E, A. A, B, C, E, A. This is the surface. This is cylindrical surface. So totally I have 5. So I am calling this as S1, S2, S3, S4, S5. There are 5 surfaces. Therefore, S is S1 union S2 union S3 union S4 union S5. So integral over S f bar dot n bar ds is integral over S1 f bar dot n bar ds plus integral over S2 f bar dot n bar ds plus similarly integral S5 f bar dot n bar ds. Let us find out one by one. First thing, integral over S. So on S1, what is your S1? S1 is OBCD. This is OBCD. This is on the XY plane. On S1, XY plane on S1, Z is equal to 0 and X will be in between 0 and 2. and y will be in between 0 and 3. So you have this is x-axis, this is y-axis, this is y is equal to 3, this is y is equal to 0, this is x is equal to 0, this is x is equal to 3, this is on the xy plane. Therefore, what is your n bar? N bar for S1. N bar for S1 is, what I said n bar? N bar is the outward normal vector. For this xy plane, this is one normal vector. For xy plane, z-axis is the normal. This is normal, but z-axis is coming inside the surface. The outward is minus k bar. So therefore, n bar is minus k bar. What is your f bar dot n bar? F bar dot n bar is, so f bar you see, this is my f bar. F bar dot n bar, f bar dot n bar is k bar. So 4x z square. F bar dot n bar is minus 4x z square. Why this minus? Because of this minus. But where is this s1? And s1, f bar dot n bar is 0 since z is equal to 0. Therefore, integral over s1 f bar dot n bar ds is 0. Let us call it s2. Now, along s2, what is s2? Here I have given s2. S2 is also a rectangle OAED. Where is this OAED? OAED is on XZ plane. On XZ plane, Y is 0. Let us, on this XZ plane, this is because this is XZ plane, Y is 0. And the outward normal vector is for XZ plane, Y, J bar is the normal vector that is along Y axis, but it is coming inside the uh, surface, therefore outward is minus j bar. So for the surface S2, n bar is minus j bar, and which is y is 0 on this. Whenever this is 0, what is your f bar dot n bar in this case? F bar dot n bar is, this is my f bar. N bar is minus j bar, so it is y square. F bar dot n bar is y square, but y is 0, therefore this is 0. Integral over s2 f bar dot n bar ds is also 0. And next is along s3. What is my s3? S3 is OAB, quadrant of the circle on the, this is quadrant of the circle on the XY plane, on the YZ plane. This is YZ plane. On the YZ plane, X value is 0. Outward normal vector is along x-axis. This is I bar, but it is inside. Outward is below. Minus I bar is the n bar. Now I want f bar dot n bar. N bar is minus I bar. F bar dot n bar is 2x square y. So along as n bar is minus I bar, and this is x is 0. X square f bar dot n bar is minus x square y. But because x is 0, this is also 0. So integral over s3, f bar dot n bar ds is also 0. So this is fourth equation. Now along s4, what is your s4? S4 is the CDE, which is the quadrant of the circle on x is equal to 2. So this is CDE, this is the surface. For this surface, outward normal vector is this. So in this direction, I bar is the outward normal vector. N bar is I bar. When N bar is I bar, what is F bar dot N bar? F bar dot N bar is 2x square y. 2x square y. Where it is, the surface is on x is equal to 2. When if I put x is equal to 2 here, 2 square is there, 4, 2 is 8y. 8y is F bar dot N bar. So along S4, x is 2 and n bar is I bar, and therefore f bar dot n bar is 8y. Actually, it is, instead of writing 8y, it is 2x square y, but as x is 2, that is 8y. Now, I need to find out integral S4 f bar dot n bar ds. F bar dot n bar ds. That means integral S4 8y ds. Now, writing this ds is different ways. Dx dy by dy dz by or by n bar dot k bar, like this. Anyway, we can take the integral. So how do you take the, I will take on YZ plane. So let us take the project. Anyway you can take it. Let us observe where it is, which is better. If this is the surface, I can take the projection on this YZ plane. If I take this projection on this YZ plane, where it falls? Exactly in this quadrant of the circle. So I am taking the projection on the YZ plane. Therefore, in place of ds, I am writing this is integral over S double integral over R double integral R 8y dy dz. Whenever I have dy dz, it is n bar dot I bar with a modulus. What is n bar here? N bar is I bar. I bar dot I bar is 1. This already I have given you here. Yes. Dy dz by n bar dot I bar. If in place of ds, I can write either this or this or this as per my convenience. I am using this. Now, n bar dot I bar is 1. Now, what is your region now? Your region is, this is y-axis, this is z-axis, and this is y square plus z square is equal to 9 is the circle. Of course, quadrant of the circle. I need to find out the limit. This is double integral. Uh, here this equation is z is equal to 0 to z is root over 9 minus y square 8 y, and z limit, these are the limits for z. Y limits are 0 to 3. 8y dy dz or dz dy. Now if I integrate with respect to z, this is integral 0 to 3, 8 comes out. Integral y is 8y, and integral dz is z. If I substitute the limits, it is 9 minus y square dy. Now I need to do the integration for this. If I substitute 9 minus y square is equal to t square, then this will become 8 times integral 9 minus y square root under square root, that will be t, and y dy is equal to minus t dt minus 2y dy. So in place of y dy will be minus y dy will be t dt. So it is t square dt. And what are the limits for t? When if I take t y equal to 0, t will be t square will be 9, this will be 3, and if I take y is 3, t is 0. So this is 8 times integral 0 to 3 t square dt. So this is 8 into integral t square is t cube by 3, that is 3 cube is 27 by 3, that is 72. Therefore, integral over S4 f bar dot n bar ds, I got 72. This is 5. And now along S5. What is your S5? Coming back to S5, I have written here. S5 is the cylindrical surface ABCBA. This is the ABCBA. What is the equation of this surface? This surface is y square plus z square is equal to 9. Cylinder. What is the normal vector for that? Along S5, y square plus z square is equal to 9. What is your n bar? N bar is grade f. F is this. Dou phi by dou x into I bar, that means 0 I bar. Dou phi by dou y into z bar, 2y z bar. Dou phi by dou z into k bar, that is 2z k bar. Because it is unit vector by root over 4y square plus 4z square. This is 2 gets cancelled. Yj bar plus zk bar by y square plus z square is 9, that will be 3 because y and y square plus z square is 9. This is your n bar. Now f bar dot n bar is 1 by 3 x part you don't get minus y square into y, that is minus y cube plus zk bar, z is 4x z square into z, 4x z cube by 3. This is f bar dot n bar. Now we need to take the projection of this. Therefore, integral over S5 f bar dot n bar ds is integral over S5 1 by 3 times minus y cube plus 4xz cube into dx. This is double integral. I need to write this double integral dy dx or dx dy. That is to be decided now. Go back to the figure. If I can take the projection on the YZ plane, I can take the projection on the XY plane, I can take the projection on the any plane I can take. If I take the projection on the YZ plane, again the projection will be on this. So because already I did for S4, now just for your convenience, I am going to take the projection of this on the XY plane, on this plane. If I take the projection of this figure on the XY plane, uh, the region will be this. This is my R2. R2 is the projection of the surface on the XY plane. I am taking the projection on the XY plane. If I take the projection on the XY plane, here this is dx dy by n bar dot k bar with a modulus. N bar is this. So this is double integral over R2. R2 is the, this is R2. R2 is the projected region, which is this. An xy plane, x varies from 0 to 2, y varies from 0 to 3. Again, a rectangle. This is x is equal to 2, this is y is equal to 3. So double integral over R1, n bar dot k bar. What is your n bar dot k bar? If I break a dot product with it, I'll get z by 3. If I write z by 3 here, then I into 3 by z, 3 and 3 gets cancelled. It will be minus y cube plus 4xz cube by 3 into 1 by z by 3 dx dy. This z by 3 is n bar dot k bar. So this 3 and 3 gets cancelled, and double integral over R2 minus y cube by z plus 4x z square dx dy. Because dx dy is there, everything should be in terms of x and y. Therefore, double integral over R2 y cube by z is root over 9 minus y square plus 4x z square is 9 minus y square dx dy. Now I need to do the integration. Of course, this is a minus sign. So this is x limits are 0 to 2, y limits are 0 to 3. This is 36x minus 4xy square minus y cube by root 9 minus y square dx dy. Now first do the integration with respect to x. 36 into x square by 2. 2 square by 2, that is 2, minus 4 y square. Integral x is x square by 2. X square by 2 means 2 square 4 by 2, that is 2, minus y cube by root 9 minus y square into integral dx is x. If I substitute the limits, that will be 2 dy. Now integrate with respect to y. 36 into 2, that is 72 into y. Y is 3 minus 8 into integral y square is y cube by 3. Y cube means 3 cube by 3, 27 by 3, that is 9, minus this integral I need to do, integral 0 to 3 2 y cube. I am writing it as y square into y by root 9 minus y square dy. I'll substitute 9 minus y square is equal to some t square. So that this is 216 minus this is 72 minus, and if I substitute this, if I put y is 0, t will be 3, and if I put y is 3, t will be 0, and this is 2y dy. Here I have 2y dy. 2y dy is minus 2t dt, and y square is 9 minus t square. This is t dt by 9 minus y with the root is t. This t and t gets cancelled, and y dy is minus 2 dt he has given. Therefore, because of that minus, I can change the limits 0 to 3. So this is 216 minus 72 minus 2 comes out. Integral 9 is this t and t gets cancelled. 9t, this is 27 minus t square is t cubed by 3. T cubed by 27 by 3, that is 9. 27 minus 9 is 18. 18 into t is 36. This is 216 minus 72 minus 36. That is 216 minus 108. This is plus 108. Therefore, integral over S5 f bar dot n bar ds is 108. Therefore, ultimately integral over S f bar dot n bar ds is integral over S1, that I got 0, and for S4 I got something like 72 if I remember correctly. Let me check it. Integral S4 f bar dot n bar is 72, and for S5 I got 108. So this value is 180. Integral S f bar dot n bar ds is 180. This is the answer for the first problem. Here the surface integrals are somewhat lengthy. Next, the next problem is find the surface integral of r bar. R bar always we know it is xi bar plus yj bar plus zk bar over the surface of the cube. 0 less than x lies between 0 and 1, y also lies between 0 and 1, z also lies between 0 and 1. It is a cube. So as I did, this also contains so many. So what is your f bar here? F bar is r bar, that is xi bar plus yj bar plus zk bar. Now what is your surface S? S is the surface of the cube. What is that cube? So this is x, y and z. So this is one surface. I will call them O, A, B, C, D, E, F, G. Now it has 5 surfaces. S is union of 6 surfaces. What are those surfaces? S1 is OABC, a square. S2, this, and I'll go the next one, this, OCDE. S3 is my OAEF, and S4 is ABGF. S5 is the front one, BCDG. S6 is the top one, DEFG. Each one is a square. Now find the f bar n bar for each one. So what is find out? I'm integral over S f bar dot n bar ds is integral over S1, integral over S2, etc. integral over S6. So instead of writing separately here itself, I am doing integral over S1. If I S1 is this, what is the equation of S1? S1 is a square, and here itself I am writing its equation is Z is equal to 0. And what is your, for the S1, what is your n bar? N bar is outward normal vector, and along Z axis it is k bar, so it will be minus k bar. What is your F bar dot n bar? F bar is your Z k bar. Here you have, it is, if I make the dot product, I'll get minus Z k bar. And along S1, what is your Z? That is 0. Therefore, this is 0. Along S2, what is S2? S2 is OCD. OCD. This is my YZ plane. YZ plane is XZ is X is equal to 0. What is outward normal vector? It is minus I bar. So it is minus X. But X is 0. So along S2 also I'll get 0. Along S3, this is my S3. OAEF. So along OAF, EF is my XZ plane. XZ plane is Y is 0 and my N bar is minus J bar. So Y is 0, therefore S3 is also 0. Now S4, integral S4. What is that S4? S4 ABGF. This is this is ABGF, this plane. What is the equation of this plane? That plane equation is X is equal to 1. What is your n bar? For outward normal vector for this is this vector, that is I bar. X is equal to 1 and n is I bar. What is f bar dot n bar? F bar dot n bar is x. X is 1. Therefore, 1 it is. 1 ds. Because it is 1 ds, where I can take the projection? I can take the projection of this on this YZ plane. So this ds can be written as dy dz by n bar dot k bar. Similarly, S5, the similar way, you will get dy dz, dz dx plus S6 is dx dy. Everything will be 1 plus 1 plus 1. Of course, the first one will be 0 plus 0 plus 0. So this value will be 3. Now find the surface integral of this over the surface z is equal to x plus y square with z greater than 0 and x greater than minus 1. The unit vector n bar has a negative z component. So this is one information he has given. So I'll so what is the surface? Find the surface integral over the surface z is equal to x plus y square. That is the surface. Z is equal to x plus y square with z greater than 0 and x greater than 1. Okay. So for the next problem, what is your f bar here? F bar is 2y plus x into I bar minus j bar. That is your f bar. Or of course, he mentioned that it is a bar. Is it right? Yeah, a bar is 2i plus x I bar minus j bar. He used that a bar for it. And surface S is given by z is equal to x plus y square. Z is less than 0 and x is greater than minus 1. This is the thing what he has given. Now, for this surface, what is the outward normal vector? N bar. N bar I need to find out. N bar is bring everything on one side and then find the derivative. If I bring all these things this side, then what is dou f by dou z I get? This equation I can consider it as z minus x minus y square is equal to 0 or x plus y square minus z is equal to 0. If I take in this way, the outward normal vector is dou phi by grade f. I need to find out dou f by dou x, dou f by dou y, dou f by dou z is 1 I am getting. If I write like this, dou f by dou z will be -1. Just to know that this is the information he has given. The unit vector n bar has negative z component. That means the unit vector should have the negative value for z. Therefore, I need to take in this way, not in this way. So that for that information he has given. Dou f by dou x is 1 I bar plus dou f by dou y, that is 2y j bar, dou f by dou z minus k bar. So I bar plus 2y j bar minus k bar by root over 2 plus 4y square. That is the outward normal vector. Now, what is your f bar dot n bar? F bar is this. Here he has given. What is a bar dot n bar? A bar dot n bar is 2y plus x into 1 by root 2 plus 4y square minus 2y by root 2 plus 4y square. K anyway 0. So if I simplify this, 2y by minus 2y gets cancelled and x by root 2 plus 4y square. This is my a bar dot n bar. Now integral over, I need to find out the surface a bar dot n bar ds. That is double integral over r. A bar dot n bar is x by root 2 plus 4y square. On what plane I need to take the projection? If I take the projection on the xy plane, that means my z is 0. If I take my z, here the equation is z is equal to x plus y square. If z is x plus y square, then if I put z is 0, x is y square, then this is the parabola. This on the xy plane, x plus y square is equal to 0 means y square is minus x. This is this parabola, and he has given x is greater than 1, so he is taking this is the region. In this region, you need to integrate that. Okay. Dx dy by, I need to get n bar dot k bar, dx dy by n bar dot k bar. What is your n bar dot k bar? This is my n bar dot k bar is 1 by 2 plus 4y square that goes to the numerator. So that is equal to double integral over r x by root 2 plus 4y square. This is my region r into n bar dot k bar is root over 2 plus 4y square dx dy. These two gets cancelled. So double integral over x dx dy, we need to do it. Limits are y, x limits are, this is minus 1, here x is minus y square, minus 1 to minus y square, and here it is minus 1 to 1. These are the limits for x, these are the limits for y, x dx dy. So this is integral minus 1 to 1. Integral x is x square by 2. If I substitute the limits, y power 4 minus 1 by 2 dy. So this is twice integral 0 to 1 y power 4 minus 1 by 2. Integral y power 4 is y power 5 by 5, 1 by 5 minus 1. So that it will be minus 4 by 5. So this is the next one is find the surface integral of this a bar over the curved surface. Only on the curved surface is asking of the cylinder x square plus y square is equal to 1, z is equal to 0, z is equal to 1. So I will explain you how to find out the here he has given x square plus y square is equal to 1 is the surface, and the f bar, I think here also used a bar. So next problem is a bar is something like xi bar plus z j bar minus y k bar, that is a bar. Surface is x square plus y square is equal to 1. This is z axis, this is x axis, y axis, and z is equal to 0 and z is equal to 1. So curved surface only he is asking. He is not asking about this. He is not asking about this. Only the curved surface in between these two. So x square plus y square is equal to 1. Therefore, what is your grade f? Grade f is 2x I bar plus 2y j bar. That is grade f. What is your n bar? N bar is the outward normal vector. Outward normal vector means n bar is grade f by magnitude grade f. 2x I bar plus 2y j bar by root over 2 times x square plus y square. X square plus y square is 1. Therefore, it is xi bar plus yj bar is the outward normal vector. What is your a bar dot n bar? A bar is this. A bar dot n bar is x square plus yz. X square plus yz. So this is to be evaluate double integral over r. In fact, this is what here integral over s a bar dot n bar ds we require. As I said, we have to take projection on any of the surfaces. Double integral over r x square plus yz dx d. This is I am taking the projection on the xy plane. If I take the projection on the xy plane, I will get dx dy by n bar dot k bar. But here in this, I don't have any k bar, so I cannot take the projection on n bar dot k bar. Therefore, I'll take the projection on the xz plane. If I take it projection on the xz plane, dx dz by n bar dot k bar, sorry, n bar dot j bar. This is your n bar. N bar dot j bar is by y I will get here. Therefore, this is double integral over r x square by y plus z dx dz. I need to convert everything in terms of x and z. Well, now, what is your region? If this is the region, if I push it on the xz plane, it will be on the xz plane. Your on the xz plane y will be 0, x square will be plus or minus 1, and you will have one xz plane is this is x-axis and this is z-axis. X is minus 1 here, x is 1 here, z is equal to 0 here, z is equal to 1 here. So this is my region R. So double integral over this region R, x square by y is root over 1 minus x square plus z dx dz. Limits are minus 1 to 1 and 0 to 1. 0 to 1 are the limits for z. X limits are minus 1 to 1. So first I will integrate with respect to x. Integral 0 to 1 minus 1 to 1 x square by 1 minus x square. I will write it as 1 minus x square. If I write like this, 1 minus x square is this. So 1 by root 1 minus x square is sine inverse x minus 1 minus x square by root 1 minus x square is root 1 minus x square. If I integrate it, x by 2 root 1 minus x square plus a square by 2 sine inverse x. Okay, this is in between. I can say this is because in even function, I can say that it is twice integral 0 to 1 plus integral zx, that is z into x. dz next. This is, I need to substitute in between 0 to 1. If I substitute between 0 to 1, I'll get sine inverse 1 is pi by 2 minus this will be 0, sine inverse 1 is pi by 2. This is pi by 4, pi by 2 by 2, that is pi by 4. And here plus z dz. Pi by 2 minus pi by 4 is pi by 4. Pi by 4 into 2, that is pi by 2. This is pi by 2 plus integral z is z square by 2, that is 1 by 2. That is pi plus 1 by 2. The similar way, you can solve these problems. Just I will give you how to find out the normal pointing outward. Z is equal to 1 minus x square minus y square. So you have for the last z is equal to 1 minus x square minus y square. This problem for the sixth one, you have a hyperboloid in this way. Outward normal vector is n bar is, bring everything on one side, it is x square plus y square plus z is equal to 1. N bar is 2xi bar plus 2yj bar plus k bar by root over 4x square plus 4y square plus 1. If I take 4 common here, x square plus y plus y square is 1 minus z. Substitute here. This is how we will find out n bar. A bar already he has given. A bar is simply r bar. A bar dot n bar ds. If I take the projection, you need to take the projection on the xy plane so that your projection r will be x square plus y square is equal to 1. So for this particular problem, integral over s r bar dot n bar ds is double integral over r. This r is this region, and find r bar you know, n bar you know, r bar dot n bar dx dy by n bar dot k bar, and then do the problem. The last problem is also in the similar way. Of course, here f bar he has given. Simply find out del cross f bar and then find n bar dot n bar. It's very a simple problem he has given. So with this, I think especially the surface integral is a topic which is to be, which needs to have more practice for solving the problems. Every problem is a some lengthy problems you'll get. You need to practice more number of questions. Anyway, I'll give you the some questions as an assignment. Practice them. So in my next lecture, I'll give you what is a volume integral. So line integral we completed, surface integral I completed. In the next lecture, I'll give you volume integral. After this, we'll see three theorems. Of course, those theorems will not have the proofs in the syllabus. Okay, prepare well and try to solve the questions given in as an assignment.